slept in today. It felt really good. I hope you managed to do the same. Let's take a look at where we left off yesterday. Okay, 2.1, the derivative and tangent problem. So we're in chapter 2, and I'm going to pause for a minute. Alright, I think we're recording again. Sorry, my family's watching TV because they can, because they've already finished their work. Okay, no, I'm good. I'm focused. So the derivative and tangent line problem we talked about on Wednesday, February 2nd, and we are going to be, there we go, just finishing this lecture today. I might do 2.2 and send it to you also, but right now the outlook's not so good. It's still snowing, and I kind of want to go outside. And yes, actually, as it turns out, I am wearing shorts. Just an update. Tangent line problem. So we talked about how we start with a secant, right? Start with a secant line, 2 points, but we let the distance between the 2 points go to 0, and we call that distance the delta x, the difference in x values. And as it gets smaller, that change in x value gets smaller, we eventually end up with a tangent line. So the formula for a secant, which we all know is just y2 minus y1 over x2 minus x1, right? It's just a slope formula. If we put a limit in front of it and let that delta x go to 0, now we have the slope of the tangent line. There we go. And the slope of the tangent line is going to be called the derivative. Alright, so the derivative of f at x is given by f prime of x equals the limit, this limit right here, the one we just talked about. Right, so it literally says the slope of the tangent line is the derivative. So instead of m, alright, we'll call it f prime of x is always going to be the slope of the tangent line at any particular value x. You could use specific value c, or you could do it in general, because f prime is also a function of x. I did I think one example from February 2nd in the notes, and those are absolutely ready for you to look at. Let me actually put in, there we go, see class notes for February 2nd for the first example from section 2.1. So where I left off with both classes, it was either in the middle of this problem or right before this problem. So I thought we'd pick it up again here. So it says, right, reading is fundamental here, find equations. So I know I want equations of tangent lines. As soon as I see this word tangent, I'm thinking I need to find the derivative. The derivative of the graph of 2x squared that passes through this particular point, 1, negative 6. Alright, let's see how we're going to do it. So first step, we're going to find f prime of x. In order to do that, we use our 4-step process. We're going to find f of x plus delta x. That is 2 times x plus delta x all squared. And this is that one I said you're going to see it so many times you just want to memorize it. This will be 2 times x squared plus 2 times 2x delta x, and 2 times 2 gives us the 4. And we'll have a delta x squared times 2. Again, horrible notation, but it's all of that delta x that is squared. Gotta get in some tea, it's still early. Okay, so from this, we subtract the original function. So we'll have 2x squared plus 4x delta x plus 2 delta x squared, and we subtract 2x squared. 2x squareds cancel out, and we're left with only things that have a delta x in them. which makes it awesome for step 3. F of x plus delta x minus f of x, all divided by delta x. So I see everything has a delta x in it. I'm going to factor it out. 4x plus 2 delta x, all divided by delta x. I love that we get colors. And this delta x can get canceled out, right? That was our whole purpose of factoring it out. Step 4, limit process. For finding the derivative, you send delta x to 0. And delta x goes to 0. That will be 4x. Okay, so this is our slope. Our slope is 4x. And you might be thinking to yourself, well, that's not very handy, because I really like to have a slope be just a number. Well, it is, kind of, but we don't know which number yet. We have no idea what this point right here is, or this one, right? We know it happens twice. So we're going to use a generic point named x0, y0. And we're going to use it just as a generic through there. But look, this line right here, right, goes through the point 1, negative 6, and through this generic point. So we know that the slope should be, subtract y values, subtract x values, and what does it have to equal? It has to equal the slope at x sub 0, right? It's still that same x value. So we can solve this in some way. Let's take a look here. If we multiply both sides by a 1 minus x sub 0, 1 minus x sub 0 over here, then our 1 minus x sub 0 cancels out, and we'll have minus 6 minus y sub 0 equals 4x sub 0 minus 4x sub 0 squared. Okay, but how does that help us, right? Well, we happen to know that this y sub 0, let me put it over here, we know that y is 2x squared, so y sub 0 is 2x sub 0 squared. So we're going to make that substitution. Right, we know exactly what the formula is. So instead of subtracting y sub 0, we'll subtract 2x sub 0 squared. And we're going to, let's move this to the other page, solve for x sub 0. Alright, so I'm going to add 4x sub 0 to this side. We'll have 2x sub 0 squared minus 4x sub 0 minus 6 equals 0. I'm going to factor out a 2. And I find that x sub 0 minus 3 times x sub 0 plus 1 equals 0. So x sub 0 equals 3, and x sub 0 equals negative 1. That's negative 1, and this point is up here at 3. So we could be sure that it's actually at negative 1 and 3, and not something like 2.75. We can find the actual x values. Once we have found our x values, we can now substitute back into, right, we want the equation of the tangent lines, find equations of the two tangent lines. So I'm going to use the point 3 comma, you see, 2x squared. 3 squared is 9 times 2 is 18. 3 comma 18, and negative 1 comma 2. And my first equation, I'm going to call it this one. Alright, let's call that A. A will be the line y minus 2 equals, what's my slope? When m equals negative 1, x equals negative 1, 4x equals negative 4. This is a fine equation. If you would rather, you can isolate the y value, or you could distribute and simplify and combine like terms and all of that. Instead, I'm just going to do the second one. So this is line B. Y minus 18 equals, well, when x equals 3, the slope of the tangent line is 4x, that'll be 12, times x minus 3. And again, you can distribute, combine like terms, and do all that goodness. Y equals 12x. You see, a minus 36 and a positive 18 makes a minus 18, actually, it turns out. So these are your two answers. Right, these are the equations of the tangent lines to this graph through that point. Right, notice one has a positive slope, one has a negative slope, and you can check and make sure we hit the point 1, negative 6 in each of these instances. All right. Yeah, that's why I didn't finish that one for one of the classes. And with 1 minute left, that's why I didn't start it for the other ones. All right, so let's find the slope of the tangent line. As soon as I see the words slope of the tangent line, I'm looking for f prime. And we always use, in this section, the limit definition. All right, limit definition. So, step 1. If it's at the given point, though, I don't know. I might use c equals 3 and g of 3 equals 2. So maybe I'll do this with 3 plus delta x. That way I'm using numbers and not variables, and maybe it'll be easier. Here's a tip. It won't be. It's still just the same nightmare algebra. 11 minus 3 plus delta x all squared. This is 11 minus, okay, so we got 3 squared is 9, plus 6 delta x, plus delta x squared. You should verify that. This would be one of those things I write on the board, and you would say, oh, wow, you're so great, Tuesday. Let me see. Now we have 11 minus 9, which is 2, plus 6 delta x, plus delta x squared. And that 2 totally makes sense, because look what we have going on here. Step 2, g of 3 plus delta x, minus g of 3. This is 2 plus 6 delta x, plus delta x squared, minus 2. And we're left with things that have delta x in them. Right? 2 canceled out. I did something wrong here. Let's make it right. This minus sign also goes to the 6 delta x, and the minus here, so that's a negative, that's a negative, 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 and this is a negative. So I'm telling you, just because we're using numbers instead of variables, 3 instead of an x, right, it's still so easy to mess these up. All right, so I'm not going to rewrite it. I want you to see my mistake, see how I corrected it. Here we go. Step number 3. We're using g. G of 3 plus delta x minus g of 3 all over delta x. Remember, we use our previous result, so I'm going to factor out the delta x. When I divide by delta x, sorry, I got distracted because I was worried that my answer wasn't going to work out, but it's good. Delta x cancels out. Step 4, we know our derivative at 3. Let's call that a g because it's g, not f. Get the right name, right? That's like calling twins different names. This is the limit as delta x approaches 0 of 6 minus delta x, which is 6. So the slope of the tangent line is 6. Fancy way of saying we find the derivative of the function at the given point. It's just a slope, slope of a tangent line. Alright, so when f is not continuous at x equals c, it's not differentiable. Okay, so if it's not continuous, there's no way it's going to be differentiable. Greatest integer function is a great example, right? This is that double bar with x that maybe some of you aren't as familiar as you should be. It is possible for a function to be continuous, but not differentiable. This is a graph with a sharp turn. And we're going to look more at functions of this type, the absolute value function. This is called I believe it's called a cusp or a corner. I call it a pointy spot because pointy spots in calculus are bad. If we have a nice smooth curve and like it's a smooth transition, then no big deal. But if it's a pointy spot, it's not differentiable. Okay, so if it's not continuous, definitely not differentiable. But it's also possible that if it is continuous, it's still not differentiable. So continuous is a bigger group of functions than differentiable. Alright, so describe the x values at which f is differentiable. I'm going to start, just like I did with continuity, I'm going to start with the domain. Because if the function's not defined, it certainly cannot be differentiable. Because we have a radical and it's not in the denominator, we know that x plus 3, the radicand, has to be greater than or equal to 0. So we find that we have negative 3 to infinity. Just a reminder, if there's an equal sign, you use the brackets. If there's no equal sign, hint hint, problem in section 1.4, you use round brackets, parentheses. Okay, so this is the domain. And so I know it's continuous on the open interval from negative 3 to infinity. Only issue is possibly at negative 3. And see, if we look, right, because we can't take this delta x all the way around, we will not be differentiable at x equals negative 3 because there's nothing on the left of it. There's no limit that we can look at from the left and from the right. So the limit does not exist. The limit being f prime of x does not exist at negative 3, and therefore it's not differentiable at x equals negative 3. Enter your answer using interval notation. So it is differentiable from 3 to infinity because it's not differentiable at negative 3, but it is differentiable everywhere else. Woo! Alright, let's do another one. Describe the x values at which the function is differentiable. Okay, so the domain says that x cannot be plus or minus 7, right? So it is not continuous at negative 7 or at positive 7. Because it's not continuous, it cannot be differentiable. At negative 7 and 7. So we look at a number line, right? Just some number line. I'm going to take out negative 7 and I'm going to take out positive 7. The best way to do that would be to take this whole negative infinity to negative 7. We're going to stop there, pull it out, negative 7 to 7, stop there, yank it out, And this will be my answer. I encourage you to put commas in between here as you enter it in WebAssign. But it will be the entire real number line except for the values -7 and 7. Alright. This is one of the ones that I mentioned that we would be talking about later with the absolute value graph. So I'm going to put it on the next page because we're going to need some space. Aren't you glad this is digital and not actual paper? Okay. Although, I'm telling you, the timber industry is making more paper every day. They're doing a great job. Consider the following function. F of x equals x minus 7. Find the derivative from the left and from the right. Now, how do we do limits with absolute values? Well, we don't. Remember, mathematicians are clever, and we sometimes clever ourselves into a hole, but in this case, we don't, because what is this function? F of x equals absolute value of x minus 7. We're going to pause a minute. Alright, so we're being clever here, and the absolute value, right? This is going to be, let me see, the absolute value of x, and then we shift it to the right 7. So over here we have a value of 7. So here's what's going on. We get x minus 7 for x values greater than or equal to 7. And we get minus x minus 7 for x values that are less than 7, right? I take a value less than 7, say 6. 6 minus 7 is -1. The absolute value of -1 is 1. And I put 6 in here. 6 minus 7 is -1. -1 is 1. Alright, so we use the piecewise defined function. So now from the left, left is less than, so it's just the slope. Remember, the slope of the tangent of any linear function is m. So from the left, I'll use all the letters. From the left, f prime of x is equal to, from the left, -1. Okay. Alright, the slope of the tangent of any linear function is its slope m. From the left, this is just a linear function with a slope of -1. If we go from the right, right, what's the slope? F prime of x is +1. So then we ask ourselves, right, natural question, is the function differentiable at 7? No. A resounding no. Our function, f of x, looks like this. Pretend that's a straight line. Our derivative looks like this. Yep, from the right it's +1, from the left it's -1. Notice the derivative does not exist here at 7 because the limit from the right is not equal to the limit from the left. Therefore, that limit doesn't exist. That limit is how we define the derivative, and so no, it's not differentiable. So even though it's continuous, it might have a pretty nasty gap in it. Alright, so that took longer than I expected. So maybe we'll leave it here. On Monday, I'm not going to be able to make it to class, so I will be recording again this weekend. I'm going to send you a recording on Monday. I will let you know. Oh, it's over here. My hair's not right. Monday and Thursday of next weekend, February, it's not December. 7th and 10th, I won't be able to be in class. Okay, so we're going to have to do this recording remote again. It's more doctor's appointments that I need to attend. Everything's going to be fine, right? We're just checking things. It's all good, just trying to get a grasp on this. But Monday and Thursday of next week, I won't be there, so we will be recording our way in, and I will send you a reminder.